Greetings and welcome to my new calculus channel. My name is John Gabriel. And today I'd like to give you a guide to the theory of fractions from book 5 for dummies. In other words, I'm going to explain all the four basic operations of arithmetic as we get them from Euclid's Elements. So there's no need for you to do any of that rot known as von Neumann's set theory construction or the juvenile piano crap axioms, because they're not actually axioms. I mean, they're just garbage. So you can actually get everything you need from the true foundations of mathematics, which are Euclid's Elements, not the rot known as set theory or ZFC. So let's begin. Now, in book 5, we realize all the arithmetic operations through the use of ratio measure. Okay, and these operations, as I've said many times in the past, are transferred to algebra intact through the abstract unit whose size is relevant. So this article that you're looking at gives you a profound insight as to why you do the things that you do in algebra. So for example, why is it that when you divide PQ by RS, the result is PS over QR? Or when you add PQ to RS, the result is PS plus QR divided by QS, okay, etc. So the most important proposition of book 5 is proposition 12. In regards to difference and addition, all that one needs is requirement 2 of Euclid's 5 requirements, not the so-called axioms as mainstream math academics think. They're not axioms, they're requirements, which states that any shortest distance can be extended or diminished. You probably haven't seen it that way, but in the form of a straight line can be extended, and therefore also, if it can be extended, it can also be diminished. And that's how you look at the operations of addition and subtraction in book 5, okay? And you use those definitions to derive both division and multiplication, as I shall show you shortly. Now, in order to understand or recognize a given magnitude or a distance of a line segment, now remember the Greeks used line segments because they were the easiest to derive from nothing. Such a line segment must be compared to another for reference. I mean, if you just, talk about a given magnitude and you don't compare it to another one, there's no way you can talk about it in any other sense, because unless you compare it to another magnitude, then you don't have any concept of what the relationship might be, whether there's any quotientness or anything else. Now, this ratio takes a scheme of antecedent to consequent, and where the distance being considered is the antecedent, okay? So we always talk about the antecedent. This is purely convention by the ancient Greeks. So, thus difference or addition measure of ratios is simplified as outlined in this diagram. So if you've got these two ratios, okay, so you've got this ratio here, and this magnitude, by the way, is not the same as this magnitude, okay, because look what it's compared to. In other words, we're talking about a very different magnitude in both cases. Here we're talking about the ratio of 1/2, and here we're talking about the ratio of 1/3, okay? And these two lines, even though they're equal, they're not referring to the same, their measure is not the same, okay? So they might be equal, but their measure is not the same. If we want to add them or subtract them, we have to use proportion, or the theory of proportion in book 5, to give them the same consequence, okay? And so if we just decide we're going to add 2 lines to this consequent, so we'll get this line here if we add it to itself twice, and the same we'll get this line if we add this antecedent to itself twice, and likewise also in the bottom, okay? So, and now we'll have that both these two ratios are described as the ones that you see on the right here. And now the way they're written on the right, it's very easy because both these are line segments. So their difference is simply excuse me, this line segment less this one, right? And their addition, simply the joining of the two line segments, all right? So to add and subtract measures, they must be expressed in terms of the same consequent or unit. And here we've made them in terms of this consequent, which is the same, right? So the difference, a half minus a third, and the sum, half plus a third, is shown in the above. In each case, the antecedent line is diminished or extended, respectively, to produce the difference measure 1/6 or the addition measure 5/6. Okay? Now, quotient measure or division is simply the ratio measure of the antecedents whose consequents are the same. So in this diagram below here, we're looking at a half divided by a third. So if we change these to the same consequent, then this is what we'll have on the right here. And then notice that in this scheme, what is being stated is that the antecedents are to one another as a consequence to one another. So given any ratios P to C and Q to C, then the ratio P to Q is a quotient of these two ratios. Why? Because P to C in ratio to Q to C is the same as P to Q in ratio to C to C. And since the measure of C to C is the unit, we have P to Q, the resulting quotient. It's as simple as that. And that's division defined for you in book 5, okay? And you can check that. Multiplication, on the other hand, is a reciprocal measure of division. In the first diagram, we see this demonstrated in this diagram here by half times a third. Now, definition 13 of book 5 is about inverting the second operand of the ratio of a ratio P to Q so that Q to P can be used as the reciprocal measure of another given ratio. And I denote the inversions in the diagram with A superscript minus or B superscript minus. So as you see over here, so we've got a half times a third. We convert them to the same consequent, and we need to, in the first case that I'm going to show you, we need to flip the second one. We invert it. As you see, it's just this one inverted to this one. And then we have that B, if we change both of these now to the same consequent, then we have that A divided by B, okay, this is going to be A divided by B, is going to give us this measure over here, isn't it? Which we see is 1/6. So that makes sense because a half times a third is 1/6, isn't it? Okay, and notice that we're measuring now in terms of the consequent because these two are the same lengths, okay? So either a half or a third can be used to measure the other, and in fact both of them have to measure the other, otherwise the multiplication is not defined, meaning that you can't have 0 as a magnitude. So in the above example, we measure a half using the reciprocal of a third. In other words, a half is in proportion to 3 sixes, a third in proportion to 2 sixes, and the reciprocal 6 to 2 is in proportion to, and I actually put a vinculum there, it should have been a colon, but anyway, it's in proportion to 18 to 6, and so the quotient 3 to 6 is in proportion to 18 to 6 is measured by the antecedents 3 and 18, okay? So because the consequents are now the same, we just have 3/18 or 1/6 as expected, since a half times a third is a 6. And then again, we measure a third using the reciprocal of 2, as in the next diagram. So what you can do is you can go over it, and you can see that this is the entire theory of the arithmetic operations, which were transferred to algebra in book 7. So what you should do is you should try all the basic arithmetic operations just described with fractions, any fractions of your choice. And remember that even natural numbers are fractions, okay? There are fractions whose consequents are the unit and whose antecedents are multiples of the unit. Be certain to read my article on book 5. It contains all the definitions and propositions of book 5, and it will give you a profound insight into the concept of number and arithmetic and algebra and the history of mathematics and why we do the things that we do in mathematics. I'm John Gabriel. This is the New Calculus channel. Till next time, goodbye.